Just don't seem to have it together during the third block. So I've got one of my son's. Actually, I'm not sure if this is Orion's Nerf gun, or if it's Walker's Nerf gun, or if it's Emmy's Nerf gun, or if it's my Nerf gun. But he didn't want me to use this one. He wanted me to use the orange one. But this is a good one. So with this Nerf gun, I'm going to shoot this piece of wood, and I guess so. You can't really see it on my table. Let me put this down a little bit. I've got another camera on it. So I'm going to shoot this piece of wood with a regular dart, like that, and then a dart that I've added a point to. Took a big paper clip and I sharpened it and shoved it in there. So when I shoot it with this, unless it's gotten dull by repeated shooting, it's just going to stick in the wood. And when I shoot it with this, it's got a rubber tip and it's going to bounce off the wood. So there are two questions for you to consider. Am I more likely to knock the board over, like that, if I use the dart that sticks into the wood, or if I use the dart that bounces off of the wood? And then why? And the second question is related to this. Which experience, well, sort of related, yeah. Which experience is a greater impulse? The dart or the board? Or do they experience the same impulse? So think about those for a little while. And I think while you consider that, I'll set up my camera. See how many cameras I can get going here on the screen. I'll move this over here. You don't really need to see the picture anymore. Oh, you know what? It's probably best. Get this down low. Yeah, so you can see that. I think I'll use this dart first. So, I would like a show of hands if you think the pointy dart that's going to stick in the board. In fact, let me just prove that it sticks in the board. I'll hold on to it. Sticks in. If I didn't have it, if I weren't holding on to it with my hand, you think the dart with the nail sticking out of it, or the point, is more likely to knock the wood over? So if you think this one is more likely to knock the wood over, raise your hand. Alright, so I see 4 on my screen. I don't know who else might be off the screen. Now, there are probably some people who just aren't involved at all. So 4 people think that this is more likely to knock the board over. How many people think that the one without the sticky point is going to be more likely to knock it over? 2? 4? So it's even, 4 to 4? It's hard to tell. Hands are appearing and disappearing. Alright, well, here we go. So I don't think that I had this. Let me zoom this in now. Actually, I'll just drag this and make it a little bit bigger so you can see everything. So I had this piece of wood here as a spacer so that when I was shooting I was the same distance every time. I don't think it really matters whether I shoot from here or whether I shoot from there. I think that the speed of this is not really going to, once it leaves the barrel, it's going to be fairly constant coming out. So I don't think that really matters. What I do think matters is how high or low I shoot this. If I shoot it, you know, if you ever tackled somebody or spent time knocking things over, is it easier to knock something over if I hit it low or if I hit it high? Which one do you think will tip it easier? Anyone?
Low.
Low. So if you want to tackle somebody and take the legs out from under them, hitting them low will do that. But if you want to knock it over like this, the higher you hit, it's actually easier. We'll get into torque probably tomorrow, maybe next week, but it's a torque issue. So if I push up here, it's easier to tip it over like that than if I push here. Now if I want to tackle somebody and take their legs out. Pushing at the bottom helps, but that's not what I want to do. I want to tip it this way. So I need to hold it equally high, and I've found a good height is about right here. So the dart, the entire dart is going to be below there, below this piece. So here goes. This is with the sticky head. Didn't knock it over. Everybody thinks you need to do things 3 times for a good sample size, which isn't necessarily true. There's nothing magical about 3. It's just better than 1. Hasn't knocked it over yet. Alright, so 0 for 3 on that one. Will this knock it over? No. No.
It's definitely moving more than the other one.
You think it's moving more than the other one?
Yeah.
Yeah, so I don't know what's changed. I definitely saw a big difference. So I think what I need to do is I need to shoot from a little higher now. Let me try the same thing, but instead of holding that right underneath the surface, I'm going to put it even with the top surface. And you know what I might be doing? It looks like I am potentially shooting downward a little bit. So this is still not knocking it over. Oh, didn't cock it. And now, do this one. Even there. Oof. Still not knocking it over. What in the world is going on? Maybe it's the direction on the table. Maybe my table's tilted funny. Oh, and I turned my board around. I bet it's the way this is cut. Sorry. Let me try this. Ah, there we go. So I'll go back to the way I had it in the beginning. I'm sorry, this is going on and on and on. So I'll put it in the original position right below the surface. That knocks it over. I'll do this again. Knocks it over. This must not be an exact 90-degree cut, but if I switch to this, doesn't knock it over. One more time. Doesn't. Okay, so I think pretty conclusively, if I want knockdown power, it's the one that bounces off. So the one that sticks in doesn't knock it down. Can anyone explain, or does anybody want to try to explain why? Why does this have less a tendency to knock it down than the one that bounces off? Claire?
Is it because the one without the nail has more surface area?
So more surface area on this.
On like the actual bullet touching the wood.
So that would relate to pressure when I was talking about helmets later on, or yesterday. When this hits, whatever force it's applying is spread out over a greater area. So if anything, that would reduce the pressure on the surface, which is why this isn't able to actually, or at least one explanation for why this isn't able to actually shove itself into the wood, because all of its force is spread out over a much bigger area. And this concentrates all of its force on one tiny little area, so the pressure is much higher for this. But I don't think that's, it's still that's kind of related to why this bounces off and why this sticks in. But why this gets knocked over when it bounces off is a different thing. So, Sophia, let me read that. It's going to disappear fast. Oh, let me open up the chat so I can see what you just wrote. You said, force is needed from the wood to push the dart back so the wood moves the other direction. Yeah, so that's one way to look at this. So there's an action and reaction thing. So this, well, okay, I'm going to step back a little bit. When this dart hits, it pushes the wood, and the wood pushes it. When this dart hits, it pushes the wood, and the wood pushes it. Newton's third law, you can't get away from it. So in both situations, the wood's pushing back when the dart's pushing the wood. So I don't know if that really completely answers it. And in both situations, the wood's pushing back. Anybody have any other insights? Riam?
I think that this thing that's on the bullet is like taking all the force from the bullet and it's spreading it out through the wood, so it doesn't apply that much force. But the other bullet, which doesn't have that, it just applies more force on the wood on one tiny area and it pushes the wood. I'm not sure.
Well, so I was thinking about what you were saying, and it reminds me of what somebody said last class, and I think they were thinking of force and time. So what they were thinking was, when this hits the wood, it's slowly, I'll use my fingers, it's slowly sinking into the wood, so the impact time is really long, which means the impact force is small. So they're saying this doesn't apply as much force to the wood because it's spending a lot of time pushing as it sinks in. And this is applying more force because it just hits the wood really quickly, so it's a bigger force over a shorter time. And that might be true if the impulse were the same. So impulse equals force times time. But in this case, the impulse is not the same. When I shoot the sharp dart at the wood, the total impulse experienced by the wood is different than when I shoot the bouncy dart at the wood. Anybody else have any? What?
Doesn't it have to do with like the velocity? Like when you shoot the
Mhm.
one with the pointy edge, like actually not velocity more than just like actually yeah the ending velocity I think. It's like when the pointy one hits, it just stops immediately.
Right?
Whereas the bouncy one like goes into the wood more because it doesn't stop because of the pointy thing. So it like there's like more. I think it has to do something with velocity. I think like the pointy one when it hits, its velocity just stops all of a
Right?
sudden.
And what happens to this one's
Whereas
velocity?
the well, this one's velocity when it hits, it goes shooting
Right.
backwards like really far. So it actually has more impact on the wood. I think it has to do something with that.
Yes. So it has to do with the change in its velocity and the change in its momentum. So this, when it hits, if you look at my screen right now, it's moving to the right across the screen. So it's got a positive velocity, and then it hits, and its velocity becomes pretty much zero. So it changes velocity by losing whatever velocity it had. If it's going 10 meters per second, then it's losing 10 meters per second of velocity. This one, if it's going 10 meters per second, after it hits, it bounces back and goes the other way. So it not only loses that velocity that it had, but it loses even more because it reverses. So the change in velocity goes from positive to negative, which is a bigger change than if you just go from positive to zero. So there are two ways to look at this, I think. I mean, probably more than that. These two things are together a closed system. So when the dart's flying out here, since it's a closed system, the overall change in momentum, there isn't any. So the total momentum of this and this, it's all conserved. In the beginning, this has positive momentum, and it loses a bunch of positive momentum, and it actually turns to negative momentum. To compensate for that, the block of wood has to gain gain an amount of momentum that that counteracts the change in this. So maybe I should say it this way. This dart has a really big change in momentum when it bounces off, which means the wood has to have a really big change in momentum in the other way. When this hits, this dart changes momentum but not by as much, which means the wood, in order to keep momentum conserved, has to change momentum too, but not by as much. Just enough to kind of make it wiggle but not make it fall over. This makes it fall over. The other way to look at this is in terms of impulse. And I don't even really, I guess I could go into that. Impulse equals change in momentum. So when this bounces off and changes momentum a lot, it exerts a big impulse on the wood. When this sticks and doesn't change momentum much, it exerts a smaller impulse on the wood. So the force times time of these two is not the same. But that's not what's asked in question number 2. The question number 2 asks, which experiences a greater impulse, the dart or the board? So for either collision, either the one where it sticks in or where it bounces off, would you say the dart experiences a greater impulse? Or the board experiences a greater impulse? Or neither, they're the same. Impulse is force times time. So just raise your hand if you think the board experiences the greater impulse when these hit. Okay, how many people think the dart experiences the greater impulse? How many people think neither experiences a greater impulse? And the answer is neither, because when this hits that, they both exert a force on one another. That's Newton's third law. This pushes that, so that has to push this, and the forces have to be the same. Can't get away from Newton's third law. And at the same time, the time at which that force, the time of impact, has to be the same for the wood and the dart. The wood can't push the dart for any longer than the dart's pushing the wood. It's just inconceivable. So the forces are the same, the impact times are the same. That's what impulse is, force times time. So I'm saying impulse is the same. It's equal and opposite. This wood experiences a force that way for a certain amount of time, and this dart experiences the same force the other way for a certain amount of time. So they experience, absolute value-wise, the same impulse. But when this hits, they both experience a smaller impulse. When this hits, they both experience a bigger impulse, because impulses change in momentum, and this dart doesn't change momentum as much. This dart changes momentum a lot. This is a confusing topic, and for a lot of people it's counterintuitive, just the idea that if you shoot something and it sticks in it, you're actually going to be less likely to knock that thing down than if whatever you shoot at it bounces off. I've heard that people who are really good at karate, if they want to break something, they don't follow through the whole time. They actually bounce, and they allow their hand to bounce off, which means the hand changes momentum more in this direction, so the wood's going to experience a greater impulse. I don't know if that's really true. I've read conflicting reports on that. Any questions about this? Okay, let's see. There are 2 things to get out of the way, but I think I'd rather change the order up from last class. I want to open it up for questions about the homework, which was the 2017-2018 Momentum and Impulse Test problems. Opening that up here. And if you looked at the solutions, for whatever reason, when I was scanning these, this last page did that. I don't know what's going on there. So it's kind of difficult to look at. Does anybody have any questions about any of the stuff on this? Any of the problems on that practice test? I've got easier to look at version here that I can just put in front of me. So these were the multiple choice. Any questions about any of this? This is your chance. If you had trouble.
Maybe number 3.
Number 3? Sure. I'll talk about it and maybe draw a picture here, and then I think I'll go to my my solutions that I had posted. But let me just sort of think through it and set it up here. So we've got a piece of putty with a mass, there's its mass, there's its velocity. So this will be the putty. I'm going to draw a before and after picture. So it's moving this way, 15 meters per second, and its mass is 0.24 kilograms. And it collides with a second piece of putty that's moving, I don't know how big this is. It doesn't say what the mass is, so I don't know. There's my second piece of putty, and it's going this way at 28 meters per second, and the mass is, we don't know. So this is the before. In the after, they stick together and they have a collective velocity of -4 meters per second. So I'll just draw them like this. Here's the first piece and the second piece, and now they're going this way at 4 meters per second, and the mass, I'll write the mass as 0.24 kilograms plus, maybe I'll just call this M. Nah, that's confusing. I'm calling it M2 here, although I doubt I call it that when I'm doing this. So that's what we've got. And this is the law of conservation of momentum kind of setup. If we have the velocities before, we have the mass of one, we have the velocity of both of them afterward, and there's only one variable we're looking for, which is the missing mass. We can solve this with just one equation, and that's the conservation of momentum equation. So what I have on the left side, this is the total momentum before the collision. There's the mass of the first putty times its velocity, and then I have the mass of the second piece of putty times its velocity. So that gives me the total momentum before the collision. And that has to equal the total momentum after the collision, which I've written as the mass of the first piece of putty times -4 meters per second, plus the mass of the second piece of putty times -4 meters per second. So I decided to calculate the momentums of the pieces of putty separately. But I could have written this down as 0.24 kilograms plus M times -4. So I could have had the total mass times the velocity. And after you do that, it's pretty much just multiplying stuff out and combining like terms and then solving. So on the left side, I've got, this is the momentum of the first piece, and what have I done here? I multiplied 0.24 times -4 over here, and then I just added that to both sides. So this 0.96 is this momentum of it's the negative of the momentum of the first piece after the collision. So I multiplied that, added it to both sides to get it over here. And then on the right, M times -4, it's what would be down here, but I'm multiplying this together, -28M, adding that to both sides. So over here I get 28M minus 4M is 24. So I just skipped a couple of algebraic steps. And finally I add these two momentums together and then divide by this velocity to get that mass. Does that clear that up?
Yes, thank you.
Sure. Is there another one that anybody would like me to explain? All right. Well, don't ever hesitate to ask. It's okay. That's why we're here. So I want to just share with you my solutions from the lab. I don't know if you watched that discussion. If you did, you've already heard this, but so you can just zone out for a little while. But I want to talk about what I was hoping you would take away from the collisions lab, which ended up being kind of lame. I haven't had a lot of practice of this, how to do remote learning labs. I don't think I did a very good job with it. But here are the major takeaways. So the flat end, this would be a so-called hard collision. And the spring end, this would be, you could call this a soft collision or a springy collision. I'll just call it a soft collision. Think in terms of hard and soft. So everything was pretty much the same except when the flat end hit, the maximum forces were really big. And that's just if I do change of momentum equals force times time, this would be an instance where when you have a hard collision, you have a short little time interval for the collision, but you have a big force. So that's why the forces are big. And when you have a soft collision, the colliding thing, its momentum has to change. That would be the momentum of the cart. You get a smaller force, but the impact lasts longer. So this force is about a third of that. But the impulse itself is not really the same. So impulse is force times time, impulse is force times time. I've kind of been implying with my math here that we would get the same impulse in both situations, but that here we would have a bigger force and here we would have a smaller force. But it's not really true. We actually have a bigger impulse here and a smaller impulse there. So the momentum is really changing more in the hard collision than it is in the soft collision. And I want to be really clear in saying there's nothing about the fact that it's a hard collision and a soft collision that makes it have to be that way. This just so happens that this cart, which has I'm going to draw this, it's got a little spring sticking out of one end. That spring is a crappy spring. It's got a lot of inefficiency to it. The force sensor, on the other hand, that the cart is running into and bouncing into, it is a spring. This is like a scale that you stand on. And when you stand on a scale, there's usually some kind of spring inside that. And your weight squishes into it and it flexes the spring, and that's how the machine knows how much you weigh. Same thing here. When this cart hits, that pushes the spring back, and that's what lets the force sensor know how hard it hit it. So this force sensor is a really efficient spring. So when the cart hits it, it bounces away pretty fast. When you turn this around and you have this crappy spring hitting the force sensor, that introduces some inefficiency, so it doesn't bounce away as fast. So that's why, sorry about this. Fire drill slides. So when you, what was I saying? When the flat side hits and it just hits the force sensor spring, the coefficient of restitution is pretty high, 0.636. When you turn it around and this not very good spring makes it bounce off, the coefficient of restitution is smaller. So this, with the flat side hitting, that would be akin to a tennis ball that you drop and it goes boing, 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 like that. And the springy side of the car hitting, that would be akin to a tennis ball that you drop that goes boing, 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 like that. So this is much springier. It retains a lot more kinetic energy. This loses a lot more kinetic energy. If we replace this, and some years we've done this, instead of this, and instead of hitting the hard end, we get a really nice high quality spring, and we hot glue it on like this. And then when it hits the sensor and bounces away, the maximum force is really small, but the impulse is still really big because it hits the sensor, it goes boing slowly, but retains a lot of kinetic energy. So let me just jump to some of these answers or questions on the back. The first one, this was just really all about showing how you can have collisions where you have a soft collision with a small force over a big time, or a hard collision with a big force over a small time. C, a lot of people when they're doing this, they just automatically expect either the impulses to be the same, or it seems like intuitively people think the soft one is going to have a bigger impulse. But that really has nothing to do with it. This collision right here, I'll bring this back again. Notice it's not exactly the same, but this ball is coming in and then bouncing back out again. And this would be an example of a hard collision with a short impact time and a big force, but it also has a really high coefficient of restitution. So you can have soft collisions, you can have hard collisions that have that are very efficient. Just depends on your spring. Finally, D. Explain how and why coefficient of restitution and impulse are closely related. So a high coefficient of restitution means a higher impulse. And coefficient of restitution is all about the ratio at which something comes in and hits and then bounces back out. If it bounces away fast compared to how fast it went in, then it's got a high coefficient of restitution. And as you saw with the Nerf darts, when something bounces off fast after a collision, it's got a higher impulse and higher change in momentum. So these two things should go up together. If this has a higher impulse than this, then this should also have a higher coefficient of restitution. And I don't know if that last question was super important, except that the only thing that would really change in this experiment by decreasing the slope is, well, the only thing that wouldn't change is the coefficient of restitution, because the coefficient of restitution is based on the quality of that spring, and that wouldn't change any. But if you lowered the slope, the cart wouldn't move as fast, so the force would decrease, the impulse would decrease. But the ratio of how fast it comes into the end to how fast it goes away, that's going to be the same. Even if it's going slower to begin with and then bouncing off slowly, the ratio of closing speed to separation speed should be the same. Alright, I'm done with everything that I really have planned for you. I just want to point out that I added an assignment. I was thinking that we would spend time together going over the multiple choice section of that test, but I think it's better for you to just work on that individually, and then we'll come back and talk about it tomorrow. It's this. So it's just 10 multiple choice questions. And then if anybody wants more practice, I didn't put this in your packet and I didn't put it in Google Classroom, but on my website, Class 33, there's another one of Mr. Pennington's old tests with answers. Anybody who wants that can do that. Tomorrow we're just going to review for the test a little bit, and then there's test on Friday. So I know some of you, there are a few of you who have some things to make up, and you're hanging out here and doing that, but the rest of you are just released, or stay and ask questions, or stay and do your tests, or whatever. Thanks for coming. Oop, stop my stream.